Good morning, everyone, and welcome to our Chapter 2 demo/walkthrough. So today we're going to be going over our georeferencing walkthrough, and we're going to talk about some of the stuff that you guys have learned about coordinate systems, datums, and projections. And so we're going to do a quick recap, and then I'm going to do a screen walkthrough with you guys in ARC. So let's get started. So, as you guys have gone over, georeferencing refers to the ability to locate features accurately. So, what we mean by that is when you georeference something, you are taking spatial information and using it to accurately represent that object or thing in a geographic space, or in this case, ArcGIS. And so the three things that we're going to go over today for georeferencing in specific are ellipsoids, and then we're going to talk about datums, and then we're going to go over the coordinate system. And finally, we will go over projections. And this information is important because conducting analysis is really difficult if you don't actually have this information, because that is what gives you spatial accuracy. So, the spheroid and the ellipsoid are generalized ways for us to actually describe the Earth. So as you guys learned in lecture, the Earth is actually shaped like a geoid and is irregular, but it's really hard to build a reference base off that. And so a lot of the times when we build reference bases, we base them off of a spheroid or an ellipsoid. And this Earth is actually not a perfect sphere, as you know, and it's actually more of a ellipsoid, in that it's kind of flattened on top just because of the way that it spins. So that brings us to a datum. And a datum is a reference or base, essentially, that describes the size and shape of the Earth given a certain measurement type. And you can have different types of datums that are based on different types of measuring. And they're specifically known as specified reference surfaces. So if you haven't noticed the theme, datums are reference surfaces. And you typically have two main types. You have a horizontal reference surface, or datum, which is anything to do with where you are in a Cartesian coordinate system. So you are at this lat and you are at this long. Then you also have vertical reference systems, and those are actually based on identifying elevation. So that would be how your elevation changes and how you measure how tall certain things are. So what you guys are mostly going to be dealing with is actually the horizontal datums. And datums consist of two major components, so the specifications of the spheroid or the ellipsoid, and then a set of points and lines that have been surveyed. So those have been measured or surveyed in a very specific manner based on the datum they are. So these will all be different. So for example, if you look at table 2.1, as you can see, they have a different semi-major axis and a semi-minor axis. And you also have different places where these are used. So for example, this one's used in North America, the Clark 18866. That is definitely not going to be the same datum as one that is used in Australia. So it's definitely something to keep in mind. When it comes to datums for the North American continent, you have three main ones that people will use. You have the North American datum of 1927, which is the more outdated one. You have the North American datum of 1983, which is the more accurate one specifically made for the North American continent. And then you have the World Geodetic System, or WGS, 1984. That one is the one that basically coincides with your typical lat-long type of coordinate system. So if you have any type of world-based coordinates, or you are trying to do something of a much larger scale beyond the North American continent, you typically want to choose that for your datum. These have all been updated several times so that you can actually have more detailed or accurate information, which is why there's a 1927 datum versus a 1983 datum for NAD. So this brings us to projections. So datums will tell us the lat-longs of a set of points on an ellipsoid, and that set or reference base will differ based on your datum. But projections will actually transfer those reference points from the curved ellipsoid that they're derived from onto a flat surface. So that's what a map projection is. It's a systematic rendering of locations on Earth onto a flat surface. And so that's where you get the different types of projections. So if you look over here to the right, you can see that the Mercator projection looks much different than, say, the Moloide or the Goods homolocine equal area projection. So it definitely comes into play which projection you use. Projections are also important because projections automatically distort whatever you are looking at. So there's absolutely no way to avoid distortion. It's just impossible. But you can have projections that do a good job of conserving certain things about your map. So, like you guys have learned, some maps will preserve area, whereas others will preserve shape. Things like the Robinson projection, which we'll go over, actually does a compromise between all four. So it doesn't perfectly preserve anything, but it does a pretty good job of preserving all four at the same time, just not perfect. So it will do a good compromise between preserving direction, distance, area, and shape. It just won't do a great job on any of them. And as you can see here, based on the three types of projection types you guys went over, they look different based on what you use. So if you use a cylindrical one, it's pretty up and down, or if you flip that, it's pretty side to side. You have the conical, and then you have the planar or the azimuthal. So those are definitely things to consider when you're choosing your projection. This is a fun comic from XCCD, and one of the things that is interesting about this comic is it actually takes a lot of the more popular projections, like the Mercator and the Robinson, and it basically gives a satirical description of the type of person you are, given whatever your favorite one is. So for example, my favorite one is the Robinson, and as you can see, I'm comfortable. I have a comfortable pair of running shoes that I wear everywhere. I think it's the best looking projection, hands down, and I do. I'm probably this person. Basically what it's saying though is the Robinson is seriously just a compromise on everything. It doesn't actually preserve anything. So this comic, while satirical, does actually give a good indication of certain things actually do have certain trade-offs. And it's also just fun. So now we're going to go into coordinate systems. So projections are the projection of the reference base onto a flat surface. Coordinate systems are actually what you use to determine where exact locations are. And there's thousands of coordinate systems available online or even that people have developed. But the most well-known ones that we're actually going to go over today too are the geographic grid or the geographic coordinate system. And then there's also the projected coordinate systems. So the geographic grid specifically is lat long. So you guys have gone over that in class or in the online presentations. And then you guys should have also covered a little bit about the projected coordinate systems like state plane or UTM. So for lines of latitude, you have or longitude, you either have the equator as the 0 point for the lines of latitude, or you have the prime meridian as a 0 point for longitude. And you use lat and long in order to determine where you are on the Earth based on a spherical coordinate system. Well, if you remember, projected coordinate systems are not based on an ellipsoid or a sphere. They are projected from that surface to a flat surface. So you actually have a different type of coordinate system for things that are projected. So this is an example of a geographic coordinate system, and we're actually going to go through a few of the projected coordinate systems so that you guys can see how that changes when you add in the projections to the equation. So let's get started on our walkthrough with ARC. Okay, so now that we've done our walkthrough through the slides for this Chapter 2 walkthrough, we're going to actually go through ARC and check out the different types of coordinate system options you guys have and the differences between a geographic and a projected coordinate system. So one of the things that confuses people the most in ARC is when you are given the option to do projections, you're given two different coordinate system options. You're given a geographic coordinate system, and you're given a projected coordinate system. So we're going to kind of talk about how those tie back into the slides we just went over. So I have here a beautiful shapefile of the world in a kind of boring color, I know. And so first off, we're going to go in and actually look at the current projection information that the shapefile has. So if you right-click on the shapefile and you go to Properties, a wonderful little Layer Properties window will pop up, and you have all these different tabs that you guys should have seen in your first labs. But we want to go to the one called Source. So this one will actually give you all the information you need in terms of where the data is saved. So shapefile is saved in this location on my computer. It'll give you information like what the type is, so if it's a feature class or shapefile. And then down here, you'll see that there is something called a geographic coordinate system. So what that means is this specific shapefile is not projected. It simply exists in a geographic coordinate system, and those coincide with datums. So if you remember what we just went over in the slides, a datum is the reference base, but it's not actually a projection of a map from a different type of aspect. So it's not conical or planar, like azimuthal. This is just a very simplistic, in this case, flat-long version of WGS84. So we're going to go over the differences in these. So first off, now we know that this is in lat-long. So this is what our map currently looks like with a WGS84 projection. And say that we want to change that. There's a couple ways you can do this. If you actually wanted to change the physical properties of the layer, which we will do in a moment, then you would actually go through the toolbar, which is right here, our toolbox. And as soon as it opens, we'll go a little more further depth into the two tools you guys will be using a lot in your next lab. So if we come over here, here's your toolbox, and if you go to Data Management, right here is something called Projections and Transformations. If you ever need to do anything in terms of projecting a shapefile, this is where you will go. So in this case, this is a shapefile. It's not a raster, so we don't want the raster project. And we already have a projection. So say that you got a shapefile that didn't have any projection information. In order for you to manipulate it, you would actually have to do what this tool is, and it's called Define a Projection. So basically, you would input whatever your shapefile is. So in this case, we'll say that one. And typically, if there is no projection information associated with it, this input would be blank. However, in this case, this is telling us that this shapefile already has a projection identified. This is going to get confusing. When I say projection in this case, I mean that it has an identified coordinate system. So bear with me. So what we're going to do, ARC is a little confusing with terminology, so what we're going to do is kind of try and clarify the differences. So we don't need a projection, or in this case, coordinate system. This shapefile already has one. So we're going to close this. And we're not going to do this just yet either, because we don't actually want to change the characteristics of the shapefile. So we will move back to this in a moment. What we're going to do right now is just look at how this changes from a very visual perspective. So that means that instead of going through this toolbox, which we again will do later, we're going to go through the data frame. So the data frame is over here on the left, and where it says layers is where you actually can get into your data frame properties. So if you right click on layers and you go to properties, you get a different window called data frame properties. And this gives you options in order to mess with anything and everything that is in here. So it affects all layers in the data frame, not just the one that you're manipulating. So for now, we're going to go to coordinate system, because that's what you're dealing with. And if you notice, we're going to make that smaller. You've got two options. You have geographic coordinate systems, then you have projected coordinate systems. You also have layers. This one will automatically give you a listing of every projection that your layers already have. So this is the GCS WGS84 that our world layer over here already comes with. Now the thing about changing a data frame is that you don't actually change the layer. So if I'm going to change the projection system in a data frame, I'm not actually going to change the WGS84 that exists in the shapefile. I'm just going to change how it's displayed. So it's not a permanent change. So when you're in the data frame, that's what you're doing, is you're making a temporary change to the data frame coordinate system. So that brings us back to the two options we have. So you have geographic, which are datum related, and then you have projected, which are projection related. So datums, once again, are the reference bases, and if you come in here, you see that you have different reference bases for different parts of the world. So you have reference bases for Africa, and there are different ones for different areas of that continent. In this case, we want a world, so you're going to go here, and this actually gives us several different options in terms of world-based datums, coordinate systems. But if you actually look closer, there's really only three. There's NSWC, there's the ITRF, and then there's the WGS84. So we're going to actually change to one of the ITRFs. We're going to do the 2000. We're going to say apply. I'm going to move this over here. We're going to say apply. And as you can see, there is a very small shift. So while this isn't a huge change when you change it, it does obviously shift the map up and down based on whichever one you're using. So projections are pretty important, even if they are temporary. So now we're going to go into a projected world coordinate system. Now a projected world coordinate system actually does require that you have a geographic coordinate system, and you'll understand what I mean in a moment. So we're going to go to world, and one of my favorites, because it's the most pretty in my opinion, is the Robinson. So we're going to say apply. And as you can see, this has actually made the world a little more curved. I personally think it looks much nicer. And it's actually a combination of different types of projections so that it doesn't necessarily preserve all aspects of maps. So it doesn't preserve area, direction, shape, or distance. But it basically compromises between all four, which is why it looks so nice. So this is really good for visual purposes. But if you look here, the geographic coordinate system used to be at the top, but now if you scroll up, you have a projection on top of that. So anytime you have a projected coordinate system, you will also have a geographic coordinate system that projection is based on. So essentially, you have a projection or you have a projected coordinate system that is based on a very specific datum. And ArcGIS automatically does this for you if you have a projected coordinate system. If you have a shapefile that does not have any projection information, which is where the define projection tool comes in, you would actually have to assign it a geographic projection first and then a projected coordinate system in order to make that stick. So thankfully for the data frame stuff, it does this all on the fly, and you guys can just visually enjoy it rather than having to worry about permanently making that change. So now we're going to go to another one that is slightly different, and I'm going to try and make these a little smaller. So now we're going to go to the sinusoidal, and as you can see, it does some really weird things to your map. So having a different type of projection is definitely important in terms of how you are visually representing something. So if you guys were to give this to somebody for a map, they may or may not be okay with it. So you definitely need to think about projections in several respects. Is it something that's visually pleasing for a map later on? Or are you actually using it for a very specific purpose? So are you using it to do distance calculations? If that's the case, then you need to use a projection that is very specific to distance. If you're going to use it for area, then you really need to choose something that will preserve area. So that's where those come in. Let's see. So then another one that comes up too is the Winkle triple, which is interesting to me. It basically, to me, turns everything into this rounded off box. But as you can see, every time that you change your projection, you do change visually how it looks. And then the thing to remember too is you're also changing how things are preserved. So in between all of these things, you may or may not be preserving distance, area, direction, or shape. And if those are going to influence your analysis in any way, shape, or form, that is something you need to take into account beforehand. So we're going to go ahead and take this all back to the geographic one, or the datum-based one, and we're just going to go to WGS84. We're going to say OK. So now we're back to where we started. And now I'm going to move the toolbox over here, because now we're going to use this to make permanent changes to our shapefile. So I want to turn this shapefile, which only has a geographic coordinate system, into a shapefile with a projected coordinate system. So we're going to double click on the project tool. This is what that window is going to look like. And so this is our shapefile that we're using. And I want to save this on my desktop so that I can find this. Actually, we will save it elsewhere so that I do not lose things. So we're going to save it here, and this is going to be our world projected coordinate system. And then the output that we're going to choose is, instead of this GCS WGS84 that we have, we're going to go back to the Robinson, since I think it's pretty. Actually, you know what? Let's do something different. Let's do the Mallowide. And then we're going to say OK. And sometimes when you transform from a geographic to a projected coordinate system, if the geographic coordinate system is not the datum that the projected coordinate system you want is based on, it will not work. So for example, say that the world Mallowide was not based on what our geographic coordinate system already is, which is WGS84. Say that it was based on NAT 83. Here, there would be a little dot that said that you need a transformation of some sort. Because datums do not actually match up with each other, sometimes you do have to do some level of transformation. In this case, we're OK. So we're going to say OK. And this will tell you when it's all completed. And we're going to go back over here. And obviously, our ArcMap did not automatically add our data, so we're going to have to go in and get it. So we're going to go here, and here it is. And as you can see, once I added the shapefile, it stayed exactly the same. So you guys have seen what the Robinson projection looks like, but now it's only coming up as what your original layer was, which was the geographic coordinate system. The reason this occurs is no matter what you add to the data frame coordinate system will not change to anything other than the first layer you add. So the first layer we added was the world that we originally started with. Because the coordinate system for that layer is WGS84, or a geographic coordinate system, that is what every single layer from here on out will be represented as. If you want to make sure that you got your projection to change, what you do is you go to Insert, and you insert a new data frame. And so now this data frame is blank, so it has no projection information associated with it. We grab the shapefile we just created with the new projection and we drag it down, and all of a sudden it is in the Robinson projection. So that's definitely one of the things to keep in mind about data frames and layers. Data frames are just a temporary representation of the data. So you can change the coordinate system, you can change the layers, you can change all of that, or the symbology for the layers, but you're not actually changing anything in the layers themselves. In order to change aspects of the layer, you have to manipulate the layer. So if we go here to the properties for this layer, as you can see now, you have a projected coordinate system as well as a geographic. And that is now part of the layer properties, not the data frame properties. So that's our introduction to dealing with projections. If anyone has any questions, please just let us know. And from here, you guys should be going into spatial data and cartography, where you guys will actually be putting more use to what kind of projections you guys choose and how you represent data in the future. So, have a great day.